Hello everyone, welcome to Keep Learning at the rate Be Creative. Today we are going to discuss a very interesting theorem of geometry. So here what it is, given two line tangent to the circle with center O at B and C from a common point A. Show that the circle passes through the incenter of the triangle ABC. So this is the diagram given. So what if the diagram would not have been given? So we can draw the diagram. Let's understand. Given two line tangent to a circle with center O. So we have a circle with center O and we are going to draw two line tangent from a point A. So the point of contact will be B and C. Now if we have connected B and C, so in this case we are going to get a triangle ABC whose incenter will be I. And this theorem says that this incenter will be lying on this circle only. So what is the concept behind this theorem is that it is relating the incenter of the triangle formed by the two tangent from the external point and the chord connecting their point of contact and the circle to which the tangents are drawn. So here you can understand that this circle is being related to incenter of this triangle. And about this triangle, you know how this triangle has been formed by the tangent to this circle only. So they are relating each other. So if you remember this relationship, it will be helpful in solving certain problems. So before moving to the solution of this theorem, you should be knowing two more theorems, that is the basic theorem related to circle. If you know, then it will be very easy for you to prove this theorem. So let's move to first those two theorems which are the basic theorems. So the first theorem says if a line segment joining two points subtend equal angle at two other points lying on the same side of the line containing the line segment, the 4 points lie on the circle, and we can say that they are concyclic. Now this is again a very important theorem in which we can prove the 4-point concyclic if this condition is satisfied. What is that condition? For example, if we have a line segment AB and we have two other points and we connect them in this way, and if you observe that the two angles subtended by the line joining this line segment and these 2 points are equal, then we can say that ABCD, that is ABCD, these points are concyclic. That means a circle can pass through these 4 points. So this is one of the theorem. The second important theorem which we should be knowing, that is that there is one and only one circle passes through 3 given non-collinear points. So if we have been given 3 non-collinear points, then there can be only one circle which can pass through these 3 points. So if you have studied about these two theorems, it's very good. These theorems are very important, and here also in proving this theorem, these two theorems will be very beneficial. Let's move to the proof of this theorem. So here what we have considered, that for triangle ABC, we have marked the angle A as theta. So if this angle A is theta and if we have I as the incenter, here you can see this is I the incenter, then we can find angle BIC very easily, which is given by 90 plus theta by 2. This is a very important relationship between the incenter and this vertex angle. So you should remember this also. Now, this angle is 90 minus theta, this angle at the incenter. Now, we have these two angles as 90 degree. That is, the radius is perpendicular to tangent, that we know. That means that OBAC is a cyclic quadrilateral. So what is ABOC is a cyclic quadrilateral as sum of the opposite angle is 180 degree. So here we can mark angle BOC as 180 degree minus theta, because since this is a cyclic quadrilateral, the sum of opposite angle will be 180 degree. So if this angle we have considered as theta, so what this angle comes out to be 180 degree minus theta. Now we will be taking a point P on the circle like this. So we can very easily find this angle as well, because we have angle subtended at the center is double the angle subtended by the same arc on the circle. So here BC arc is subtending angle O at the center and same arc is subtending angle P on the circle. So it will be half of that. So it will be 90 minus theta by 2. So half of 180 minus theta, it is 90 minus theta by 2. Now if we have a triangle ABC, let's move back to the triangle ABC. So if you remember that at incenter, that is at point I, we have seen that this angle is 90 plus theta by 2. This we have already mentioned. Now you can see that angle BPC plus angle BIC, what it is? It is 90 minus theta by 2 plus 90 plus theta by 2, which comes out to be 180 degree. So if you see, focus on the quadrilateral BPCI. So in that case, BPCI will be a cyclic quadrilateral, as the sum of the opposite angle is 180 degree. Now, if this is a cyclic quadrilateral and we know that there can be only one circle passing through three non-collinear points. So here the points are B, P and C. From these 3 points there can be only one circle, and which is this circle which is being drawn here. So if this condition is there, then in that case what we can say that this point I should lie on this circle only. What was I? I was the incenter of this triangle. So where it has come? It has come on the circle. So that is what we need to prove. For two line tangent to the circle with center O at B and C from a common point A, the circle passes through the incenter of the triangle. So I hope you must have enjoyed the theorem. This is a theorem which can be used in many geometrical problems, where, as I told you, what is this relating? It's relating the incenter of the triangle ABC and the circle with center O and passing through B and C. So this is a very interesting theorem. So if you have liked the theorem and you want to see some more problems like this, please like and subscribe the channel and like the video. You can also share this video with more geometry lovers. Thank you.